Okay, good morning. All right, that's not good. This Friday before a long weekend. I was expecting a little bit more energy here. Good morning. Okay, that's acceptable. That's acceptable. Okay, so we're going to look at section 14.8 today. We're still dealing with maximum and minimum, but this time there's a little bit different condition imposed. So in 14.8, we're going to look at something called the Lagrange multipliers. What this is a method to solve a constrained maximization or minimization. Okay, so we're still looking for the biggest and smallest of something, but this time there is a constraint attached to it. For example, suppose we want to maximize this function. Now, normally by itself, we know what to do. You find the critical points, you do that d-test. Now, this time we're going to add something to it. We want to maximize this function subject to the constraint that whatever x and y are, we require x times y to be equal to 1 at all times. Okay, so this is a statement of a constrained optimization problem. You want to optimize certain things, but now there's a condition. You can't arbitrarily choose x and y anymore. They have to obey this condition. If x is 10, then y has to be 1 over 10. Things like that. The function f this thing is called the objective. That's your goal. That's what you want to do. You want to maximize and minimize whatever it is. X, y equal to 1 in this example here. This is the constraint. And this is a condition that x and y must meet. Okay, so that's the kind of problem we're investigating here. Okay, let's look at geometrically what we're dealing with. Let's look at the level curves of the function f. What shape do we get? What are the level curves? Circles, right? X squared plus y squared is equal to k. So those are circles. So we got a bunch of circles looking like that. Oh, that's a horrible. You get the idea. That's a circle. Right? So these are different circles we got. Let me fix this up a little bit. All right. Much better. And this one out here, right, the bigger the k, the bigger the circle. So this one might be k is 100, and the one down here might be k is equal to 1 or something. For example. What about xy is equal to 1? If I were to put xy equal to 1 onto here, what shape do I get? Hyperbolas, very good. This is y is equal to 1 over x, right? So these are hyperbolas. And they look something like this. Sorry, this shouldn't cross the x-axis there. It lives entirely in the third quadrant. So what this is doing, what we're doing actually here, is we are constrained to travel on these two green curves. The constraint. This is the path that we are forced to stay on. Imagine if you're climbing a mountain, and the mountain is very, very rugged, very dangerous, and you are only permitted to travel on the path that has been set up prior to your arrival. That's what these green curves are. You can't get off the trail. You have to stay on that. And now you have to stay on the path here, and you're looking for the highest peak, highest point, or the lowest point, either one. So that's the idea here. Well, we have to stay on that. While we look for the maximum or the minimum of f of x, y. All right, does that make sense? Yes? Okay, good. Now, how do we do this? What's that? Oh boy, look at that. Aha. All right, there we go. Now, one thing you want to notice here, notice that, look at the first quadrant portion of the level curves we sketch. Notice that the maximum or the minimum can be achieved whenever that constraint curve is tangent with a level curve. The reason is because if it's not tangent, then I can move on the, let me bring this back here. Imagine if I'm at this point, my level curve is not tangent to my constraint curve. That means I can move a little bit to the right or to the left of that point and find a higher k or lower k. But if I'm over here, notice that if I move to either side, I'm going to get a k value that's either higher or lower than what I got here. So in this case, notice that k is equal to 1. If I move to either side, I'll get a bigger k. In other words, I cannot get a lower k than at this point, at k is equal to 1. Do you see that? Same thing happens here. Whenever the constraint curve is tangent with a level curve, that's where we have a maximum or a minimum. Any other location, you're allowed to move along the path to get another value of k. So that's the key point here. Notice that the max or the min of f of x is where the constraint curve is tangent to the level curve. If two curves are tangent to each other, that means that their gradient vectors are either pointing in the same direction or in the exact opposite directions, right? This means their gradient vectors are either in the same direction or in opposite directions. Make sense? Yeah? Does that make sense geometrically? That's the key here. They have the same direction or opposite direction, but they don't necessarily have the same magnitude. So if we call the constraint curve g of xy, and f of xy is whatever we're dealing with, remember this is our objective, then we want to find all the locations where the gradient vectors are aligned or in opposite directions. That's the goal here. The gradient of f is equal to, because they may have different magnitudes, so that means that one of them is going to be equal to a constant multiple of another. And the constant we always use is the lowercase Greek lambda. So that's lambda, lowercase Greek lambda. And this thing is called the Lagrange multiplier. All right, so this is the key equation. Once we find out all the locations where this happens, then we just compare the values of f. Whichever is the greatest one is the maximum, whichever is the lowest one is the minimum. Just like what we did with the D test, actually the absolute max and min. Then compare f of xy to find the max and min. Okay, so that's the idea. Lagrange was a French-Italian mathematician. He lived during the 18th century, who did a lot of work in physics, in mechanics, dynamics, and of course has a lot of contribution to calculus. All right, so let's try this out. This is what we need to do. Once we can solve this, we can find out where the max and min are. And let's just solve this example I started with. The goal here is to maximize or minimize x squared plus y squared. The constraint is that x times y has to be equal to 1 all the time. All right, so first of all, we're going to define g of xy. That's always our constraint, is equal to xy, which is equal to 1. F is our objective, g is the constraint. Now I want to solve this equation. The gradient of f is equal to some constant lambda, the Lagrange multiplier, times the gradient of g. Gradient of f, so partial with respect to x, gives me 2x in the I direction. Partial with respect to y gives me 2y in the j direction. Right-hand side, there's the Lagrange multiplier. We don't know what it is yet. Gradient of xy, partial with respect to x, gives me a y, so that goes in the I direction. Partial with respect to y gives me x, and that goes in the j direction. Okay? Okay, now this will give us two equations. First equation says that 2x is equal to lambda times y. We'll call that equation 1. Second equation is 2y is equal to lambda times x. Call that equation 2. Notice that our problem, we started with 2 variables, but now we have 3 variables. X, y, and lambda. But we don't really care about x and y. Lambda is kind of like a helper variable here. We don't care what it is. As long as it is something that helps us solve the problem, we don't care what it is. We really want to know what x and y are. So we introduce one more variable, but that's a variable we can kind of throw away. It's just there to help the problem moving along. Okay, now the next few steps can be a little bit tricky. Notice that if lambda is equal to 0 in either 1 or 2, then the right-hand side of both equations will be 0. Look at the first equation here. If lambda is equal to 0, then x has no choice but to be 0. Do you see that? If lambda is equal to 0, then x or y, possibly both, have to be 0. Is there a problem with that? What's the problem with that? Right, the constraint is not satisfied, right? If x or y is equal to 0, then x times y can never be 1. But this violates the constraint. Xy is equal to 1, which is a requirement. Xy is equal to 1 says you can choose whatever x and whatever y you want as long as they multiply to be 1. But if either one is 0, then you're breaking the rule. You can't do that. And therefore, this implies that lambda cannot be equal to 0. If lambda is not equal to 0, then that's okay. That means we can solve for lambda, divide by lambda, or whatever in these two equations. And by the way, we still don't care what lambda is, but we know it's not 0. So that's all we care for now. If lambda is not equal to 0, then what we can do is we can divide equation 1 by equation 2. I'll divide the left side, and then I'll divide the right side. So we get 2x over y, 2y is equal to lambda y over lambda x. And so this tells me I can cancel the 2's, I can cancel the lambdas, and then I can cross multiply. So this tells me that x squared is equal to y squared. See that? Okay, good. Or we can also say that y is equal to plus or minus x. So now we can substitute this into the constraint equation, and then we can solve for x or y. Okay, so here's our constraint equation. xy is equal to 1. That means x times plus or minus y must, that means x times y, but y is with this guy, right? So that says plus or minus x squared is equal to 1. But we also know that negative x squared is a false statement. This can never happen. So this implies that x squared must be equal to 1. Okay? Which means that x is equal to plus 1 or minus 1. All right, so we found out the x locations where the maximum and minimum can occur. Now we got to collect the y values. So, how many points do we have here? Knowing x is plus or minus 1 and y is plus or minus x, how many points are we going to be looking at? Two or 4? The two choices here, so why not 4? Because x times y has to be equal to 1 implies that they have to have the same signs, right? X and y must be both positive or both negative. So that's another very important observation we need to make. If they have different signs, they will never multiply to be 1. So 2 points to consider. X is plus or minus 1. And y has to, that's a negative one, sorry. And y is the same number, and also is going to have the same sign. So we got 1, 1, we got minus 1 and minus 1 to consider. All right? Okay, now we find out what's going on at f, at these locations for f. F of 1, 1 is 2, and f of minus 1 and minus 1 is equal to 2. So they're the same number. Are these going to be the maximum or the minimum of f? And how do we know? What do you think? Yeah. Maximum? Okay. Who thinks it's a minimum? You think it's a minimum. Why do you think it's a minimum? Very good. He said that if you look at the level curves we sketched earlier, remember we're constrained to staying on the path here. And notice that the bigger the k, the bigger the value of f, the bigger the circle. So if I'm allowed to stay on here, I can just go either direction as far as I want, and as long as I keep going, I'll keep finding a bigger k value. You see that? And the smallest one I could ever get is down here. I can't get any closer to here. So this one right here is the smallest possible value I could get. But I can always find a bigger value by keep going either direction. So these will be minimum values. Another explanation, which I'll write down here. Another way to look at it is that we know x times y has to be equal to 1. So that means x times equal to y means either can be made arbitrarily large. For example, I can make x 1 billion, and I can make y 1 over 1 billion. And if either of these is 1 billion, then this is going to be a huge number. See that? And I can make x 10 billion if I want, then y has to be 1 over 10 billion, and that just makes this really, really big. And x squared plus y squared is therefore very large. Large. Without bound. All right? Questions? All right, let's do another one. Now, these problems, as you saw, can be a little tricky when you're making these reasonings. So that's really the hard part. The gradient and all that stuff, that's not difficult. It's the reasoning behind all of these, interpretation of what the equations tell you that can be challenging. Okay, so let's check this one out. The same method applies no matter how many variables you get. Let's look at a 3-variable function. So let's find out the maximum and the minimum of x, y, z, subject to the constraint that x squared plus y squared plus z squared is equal to 1. And once again, that constraint equation is your g, which is always equal to a constant, 1 in this case, but it's always equal to some kind of constant. You take the equation equal to a constant, make that g, and that's what you got. Then remember this key equation. Everything falls out of this equation. And again, geometrically, remember, this is saying that the gradient vectors are either aligned or going in opposite directions. That's what we're doing. We're dealing with 4-dimensional objects now, so we can't really picture that or visualize that. But imagine in 4 dimensions, and these guys have their gradient vectors, we're still wanting them to be aligned or opposite to each other. All right, let's get this down here. gradient f, that should be easy, yz, xz, and xy equal to constant gradient of g, 2x, 2y, 2z. Last time we had two equations because we had two variable functions. Now we have three equations. If these are four variables, then you have four equations. Of course, things get more complicated as more equations show up, but the general idea, the general process is identical. And once again, I'll label them 1, 2, and 3. Okay, now here's going to be a little bit of conceptual mental gymnastics here. Just like last time, we're going to first examine if lambda is allowed to be 0 before we do anything else. If lambda is equal to 0 in any of these equations, say the first one, that means one of the three, at least one of the three, has to be 0. Do you see that? In any of these equations, lambda equal to 0 requires at least one variable to be 0. But that's still okay because it can still satisfy the constraint, right? If you make one of these 0, even if you make two of these zeros, you can still satisfy the constraint. Okay, so this one so far looking like that lambda could be 0. Okay, fine. However, if lambda is 0, then f is always going to be 0. You see that? Which means but notice that we could find combinations of non-zero x, y, z. So f is positive or negative. Right? If I have this equation here, you can, in principle, come up with a bunch of different sets of values such that this will either be positive or negative. If two of these are negative, then this will be positive. If one of these is negative, then this will be negative. Do you see that? Which means f is equal to 0 is neither going to be a maximum nor a minimum because of this fact here. Make sense? You see the reasoning here? Yes? No? Yes? No? Nod your head if yes. Okay, good. Which means f equal to 0 is neither max nor minimum because I have ways to make f equal to a positive number which is automatically bigger or a negative number which is automatically smaller. So 0 is not going to be a max or min, which we therefore don't care about. So lambda is equal to 0, even though it's allowed, is not going to be something we're going to consider. So once more, we're going to assume that lambda is equal to 0. And now we can do a bunch of different things with the three equations. For example, from equation 1, notice that I can say lambda is equal to yz over 2x. Right? I just divide it out and I get yz over 2x is equal to lambda. Then I'm going to take this into the second equation. Second equation says xz is equal to lambda y, lambda times 2y. So xz is equal to lambda times 2y. We can eliminate the 2. We can eliminate the z. And then I can multiply the x over here and multiply the y's together. And I get x squared is equal to y squared. And I'll call that equation 4, and I'll come back to it. For now, I don't want to do anything to it. What this accomplishes is that I know the relationship between two variables now. And I want to find another relationship between another two. And that allows me to tie all three together into so I can solve for one of them. And I'm going to duplicate this process again, this time with equation 2. From the original equation 2, we see that lambda is equal to xz over 2y. And then I'm going to take that into equation 3. I already used equation 1 to come up with something, so equation 1 cannot be used again. If I use equation 1 again, I will find out the same information that I already have. So I'm going to use another equation which I have not yet used. Going to equation 3 now. Equation 3 says xy is lambda 2z. So that says xy is equal to lambda 2z. And a very similar thing happens here. The 2's go away, the x's go away, and then when I multiply y over and then multiply the z's together, I get this new equation, which I'll call equation 5, and again, leaving that alone just for now. Okay, so far so good? Yes? Nod your head if yes. All right, good. Now, looking at equation 4 and 5, what else can we deduce from those two things? X squared is equal to z squared, right? So 4 and 5 tell us this very important thing here. X squared is equal to y squared, which is equal to z squared. So the square of these three variables simultaneously are going to be equal. They can have different signs, but if you square them, they will all be equal. All right, knowing this, we can go back to G. That's the equation. You see, notice the procedure here. You use the gradient equations to find out relationship between x, y, z. Then you take that relationship into G. And then you come up with one variable at a time and then get the other two. All right, so G of x, y, z is x squared plus y squared plus z squared is equal to 1. But we just found out that they're all equal. So this is equivalent to 3x squared is equal to 1, right? So this says that x is equal to plus or minus 1 over radical 3. What about y? What can we say about y? Same thing, yeah? Because y squared is x squared. So 4 says that y is plus or minus. So this also implies y is plus or minus x. This implies that z is plus or minus y, right? So if y is plus or minus x, then y is exactly the same thing. What about z? Same thing? Yeah? So, okay, so this is from 4. This is from 5. Knowing x from 4 and 5, we get these two conditions. All right, now how many points are we considering? Each of these can be 2, and there are 3 of them. Do you remember how to do permutations? You have 2 choices, and there are 3 positions. So how many possibilities are there? 8. Yeah, 2 to the third. Each time you can, if you fix 1, you can vary 2 in 2 choices. So there are actually 8 points. 8 points. 2 times 2 times 2. Yeah, 8 points. All right, so listing these will be a little bit of work. So let's list the obvious ones. All positive. And then all negative, right? These two are obvious. Then we're going to list when one of them is positive, the other 2 negative. And there are 3 ways to make that combination. So here we're going to get 1 positive, 2 negatives. And all you do is here, you just shift the location of the positive number, and then you'll get your 3. All right, so we got all positive, all negative, 2 negatives, and then we do the same thing this time with 2 positive. And you collect them exactly the same way. We want 2 to be positive, so let's make the first 2 positive. And then you just keep shifting the location of the negative one, and you get the other 2. Let's see, this guy up front. Yep, here we go. All right, now we got our 8 points to consider. Right? All positive, all negative, 2 negative, there are 3 choices. 2 positive, there are 3 ways to make that happen. And there are the 8 candidate locations. And now what do? We check F at all 8 places, right? It's actually not that difficult. F is just X, Y, Z. And very obviously, the maximum is when 2 of those Well, the maximum is when all three are positive or all three, or at least two. I'll just write it down. The maximum is when this is positive, which happens when they're all positive or when two of them are negative. So the first and second row of those 2 8 points we collected will give us maximum points. So that's going to be 1 over radical 27, is that right? 1 over radical 27. And these are first 2 rows of the candidate points. Candidate points. You can think of them as critical points. They're essentially the same thing. The minimum occurs when this is negative, which happens when only one of them is negative, and that happens at the bottom row of the candidate points. Negative 1 over radical 27, and that's the last row. Oh yeah, and first row except all negative, you're right. Last row and all negative. Yep, you're right. Absolutely right. All right, so that's what we have to do. All right, one very quick thing. We won't work through this all the way because we actually did the same problem last time. But we're going to revisit the problem we did last time. We want to find a point on the plane 3x plus 2y plus z equal to 6, closest to the origin. Now, from the perspective of Lagrange multipliers, we could solve this problem. Because what this is saying is that we want to minimize the distance from some point to the origin, x squared plus y squared plus z squared under a root, right? Subject to the constraint that these 3 points stay on this plane. So that's our constraint. Okay, so last time what did we do? Last time we worked with just the distance equation, but we used the plane equation to eliminate, I think, z, right? We eliminated z, and then we did the partials and all that good stuff. This time we can look at things in a different way. We work with this equation, leave all 3 variables in, and then introduce a constraint. Then we just do gradient f equal to lambda gradient g. And you'll get exactly the same result. It's the same problem. It doesn't matter how you approach it. It's the same problem, but you get the same result. So the point of this is that you have now a choice. Whenever you're working with a problem like that, you have an additional choice that you can consider. Do you want to work with Lagrange multipliers, or do you want to substitute and get rid of one of the variables? There's pluses and minuses in each method. You have to look at that and make that judgment call. All right, that's it for today. Enjoy your long weekend. I'll see you again Wednesday. Yeah?
hassle that we're going through, can we just find maxima and minima like we did like the very first time and then subject the points to the constraint?
Yeah, you could. You might, like here. here you could just solve for y is 1 over x and plug into here, and then just work with it with the last time. But that may not be as easy to do. For example, when you get to here, there's going to be z is equal to radical 1 plus x squared plus y times x times y. That may be a little bit difficult. On the other hand, the good thing is that gradient is easy to find.
Correct.
So the choice here is this is easy to do. These may be difficult compared to eliminating that, and then you deal with difficult partials. So like I said at the end, that's a judgment call that you're going to have to consider and decide which way to go.
Cool. Thank you.
Yep.
I just wanted to ask if we would ever see a problem where Lagrange multiplier would be 0.
It's possible.
Okay, because that would be comparing the direction of two zero vectors, and I thought the zero vector had infinite direction.
It can happen, but usually that's signifying that something is breaking down. Maybe perhaps there's a discontinuity somewhere that this graph is not, that the surface or the object we're dealing with or the path is not behaving very well. Because in that case, if lambda is equal to 0, basically we ignore the constraint altogether. Yeah. We're just saying that gradient f is 0. And something weird is, it can happen. But that's usually, most of the time when we're dealing with like polynomials, it's not going to be 0. Or at least 0 is not going to give you a meaningful answer. But if you're dealing with like a log of something, maybe then you have to examine that possibility. If something is acting really weird,